thank you for organizing this workshop. It's nice to give a talk where a lot of these ideas were originally developed. So I'm going to talk about Hubbard models for non-relativistic odd-parity spin splitting. By non-relativistic, I mean no spin-orbit coupling. And then by odd-parity spin splitting, I mean that in a particular point in momentum space, spin up and spin down have different energies. And then when we go from k to minus k, that energy difference changes sign. Okay. All right, and so I'm going to focus on work in these three papers. And before I jump into it, let me just acknowledge the people who have carried out the work on those three papers. So I benefit a lot with collaboration from the Copenhagen group, so Brian Andreas, and then more recently with Morten. We have our local DFT colleagues who provide us a lot of information. But then the work done today was first in the minimal models. That was undertaken by Merce, so she did most of the work there. She was a PhD student of Brian's at the time, and she's now a postdoc with me. The odd-parity magnetism, that was carried out by UAU, who's a postdoc with me, but now he's moved to Minnesota, and he's working with Andrei Chubikov. And then more recently, largely spearheaded by Morten, we'll talk about the development of this H-wave spin texture in this iron arsenic-based material with phosphorus. Okay. And I do have 2 postdoc positions available, so if you're interested, just email me. Okay, so I'm talking about spin splitting, so it's useful to go back to understand where that comes from. And the key to that is time reversal and inversion symmetries. So throughout this talk, I'm going to assume that my non-magnetic state has both these symmetries, and then we'll go into magnetic states that develop out of that. Time reversal and inversion are both symmetries in momentum that take k to minus k. Inversion doesn't change spin, and then time reversal flips spin. If we have both these symmetries, we of course have the product. And because time reversal is an anti-unitary operator, when we square this, we get -1. This is a symmetry that keeps k invariant, and that means at every k, we have a 2-fold Kramer's degeneracy coming from this. And so if we want to remove this Kramer's degeneracy, which we call spin, we have to break time reversal times inversion. And so we can do this in 2 ways, and we've been hearing a lot about these 2 ways of doing it. One, we can break time reversal while preserving inversion, and that gives us altermagnetism. And so here's a D-wave altermagnet, and we've seen pictures like this quite a bit already. The other way, did I hear a comment? Oh, you have a comment?
Yeah.
Ah, okay.
I don't know if you're going to pick. It's not only it is altermagnets with inversion broken.
Yes, I know.
Okay.
I know.
Okay.
But
I just wanted to.
And we can do that, but then I
Just want to make it generalized.
yeah. So it is a lot of that is generalizable when inversion's broken, but it just makes it too much to talk about.
Yeah,
All right. So then another possibility is we break inversion and preserve time reversal, and that gives us odd-parity magnetism, which I heard is also called anti-altermagnetism now. Is that? Yeah.
Can you clarify? I hate to go back to this discussion yesterday. Actually, I don't hate. I think it's going to be fun. But when you say preserve T, you mean preserve T times translation or really preserving T?
So here, no, it's fine. It's
Actually, it's a legitimate question. I'm not.
So right now, in this example, I am legitimately preserving T, and there is no magnetism per se. But then later, I will talk about magnetic states that break T, but also have this kind of odd-parity magnetism.
You can see that I have a bad influence on my colleagues.
It can be a ferroelectric. Yes. Yeah. Yeah, but in this case then, before we have any magnetic order and we have inversions broken and time reversals present, then we know that we have, in principle, a Rashba-like spin-orbit coupling is a well-known example of this. And then you can see that the spin splitting is of opposite parity from one side to the other. Okay. you can have L equals 3 here, and I will be talking about even L equals 5, right? So we'll have examples of that, but yes. So that's what I mean. Just generally break inversion symmetry and preserve time reversal. That's true, yes. I can just lean. Yeah, you can speak in mind. All right, so that's spin splitting. And now I'm going to go over some things we've gone over quite a bit already in this conference, so I probably don't really even need to sign. But we're interested nowadays in non-relativistic spin splittings when we can separate spin rotations and space rotations. And one very common example we see here is we rotate spin by a 2-fold rotation and space by a 4-fold rotation. This stabilizes our D-wave altermagnets. And if we have spin-orbit coupling, these 2 rotations would have to be the same. So here's an example of a non-trivial example of one of these spin rotations. And we've heard, as was developed here, that if you consider collinear magnetic states in the presence of these spin and spatial decoupled transformations, you find 3 types: ferromagnetic, anti-ferromagnetic, and altermagnetic, with their characteristic 3 spin splittings. This has a uniform in momentum spin splitting, this has no spin splitting, and this has this D-wave-like altermagnetic spin splitting. Okay. And the key point is that the non-relativistic allows for this spin splitting to be extremely large, much larger than relativistic effects. And so that's why we become interested, not just because this is large, but also there turns out to be many materials. But a typical number could be 100 MeV easily. Okay. And we've also found more recently that even in this limit, you can have non-collinear states that also have spin splittings. And one example we've heard about is P-wave magnetism in the cerium nickel arsenic oxygen, where here you have a coplanar magnetic state, so the 2 ceriums have moments in plane that are orthogonal to each other. And then that leads to a z-axis spin splitting that is odd parity, so plus here and minus here. And in fact, all these possibilities have been classified in 3 PRX articles last summer, where they find something like more than 100,000 spin space groups. And you can understand which ones have spin splittings, which ones don't. And I'm not going to talk about the symmetry origin of all these, but our focus here is really to create minimal Hubbard-like models so that we can have microscopic models for these spin structures. So that's our goal. Okay, so if we're going to develop minimal models, the first thing you should do is ask, are there minimal models already? And indeed, we've already heard about this a few times. There's some well-known minimal models. And so this is Kanjin Wu. Yeah, he said that. We already have a minimal model. And I guess I should have your picture here too, Eduardo. But,
Like you said that.
Yeah, but here, I also borrowed from your talk and put in some earlier references that I wasn't aware about. But the idea here is relatively simple. We have a single Fermi surface with 2 spin species, up and down. And then we can imagine that we have some instability of that Fermi surface, where the spin up and spin down take different Fermi surfaces. And that instability is well known to us in the context of a Stoner instability. So this lies behind all our Stoner instability theories. But of course, we can do that in a way that's not uniform for a ferromagnet where the Stoner instability applies, but rather we can make it momentum dependent. And so we can get from that D-wave altermagnetism, and we can get this odd parity magnetism coming out as well. And because this is driven by interactions, not by spin orbit, of course, we can have large spin splittings from this. And the thing I want to point out, which I think is different from what we do today, is that in these models, the spin splitting is the primary order parameter. When you write it down, you solve a mean field theory for that spin splitting. But as you may have gathered from listening to all the talks, really in our cases, we have some sort of nail order, which is the primary order, and then the spin splitting comes as a secondary, or I think there's some better language for that. What was the word? Primary?
Vestigial?
Pseudo-primary order. But it comes induced in some way by the presence of this nail order. And so when we want to make our minimal models, we want to capture that physics. And so that was one of our central goals. All right, so I'm going to show you what our minimal models are like, but you've already seen this also many times, especially this morning. So from Raphael and Jorn. But here, I'm going to choose the favorite. This is the Lieb lattice model. In our language, we call this the model for space group 123, which is a square lattice, and Wyckoff position 2F. Because we're going to have, what? Lieb lattice sounds nicer, but we have 40 of these models, and so we have to choose Lieb 1, Lieb 3, 40. So it's easier to label them this way. So the key ingredients to all these models are the space group and the Wyckoff position. Wyckoff 2F is exactly this position on the corners of this square. This is a simple square lattice. And then we're going to have two atoms per unit cell, one spin up and one spin down. All right, so to see the form of these models, or what these Hamiltonians look like, and to give you an idea of what we do, okay, we're going to have sublattice degrees of freedom characterized by Pauli matrices tau, and spin degrees of freedom characterized by Pauli matrices sigma. And here's a Hamiltonian that you've seen a few times today. We're going to have some generic hopping term that we're not going to pay much attention to. We're going to have a hopping between the magnetic ions characterized by this Tx. And then we're also going to have a self-consistently determined RPA nail order. And so we can do RPA theory with all the parameters and see if this is a self-consistent solution. And when it is a solution, then it has some order parameter symmetry associated with this. And this I'm borrowing from McClarty's PRL on Ginzburg-Landau theories. So there's going to be a spin vector, and of course a sort of spatial symmetry associated with that. And this spatial symmetry we're familiar with. We call that S wave, D wave, G wave, etc. And then in this particular example, this gamma n is B1G, and it's this D wave altermagnetic state. Okay. All right. In addition, we have this important term in these models, which we call the asymmetric crystal hopping. It has a tau z, and this tau z turns out to have a non-trivial symmetry. And in fact, when we put electronic s orbitals on these sites, this tau z always shares the same symmetry as this gamma n. So these two, this has gamma n symmetry, and since this Hamiltonian must be invariant, that means that the momentum dependence of this term must also have gamma n symmetry. So it carries that same symmetry. Okay. So just to give you a feeling of what these look like, and for some of the things that'll be important a little later on, here's our nearest neighbor hopping term, written in a particular Fourier gauge. And we choose this Fourier gauge because writing this Fourier gauge allows us to assign definite symmetries to these tau x and tau z operators. But it comes at a small cost. We get this kx over 2, ky over 2 like terms. And that means that this is not invariant when we add a reciprocal lattice vector to k. So if I add 2 pi to this, I pick up a minus sign, right? But this structure will end up playing a small role later on in the odd parity case. And of course, for here, this is a D-wave altermagnet. It must have this symmetry, and so TZ must have this form. So it just corresponds to a hopping that's a different sign this way and this sign. So this has been called the Lieb lattice model as well. All right, and I'm not going to focus too much on altermagnets because Brian is going to talk a lot about those. But let me just point out one thing that pops out right away. This Hamiltonian is sufficiently simple that you can get all the eigenstates. There's 4 bands. Right? And we can ask, when are some of these 4 bands degenerate? And you can see there's a plus or minus sign here. So when this Tz of k is 0, then we get a degeneracy between 2 of those bands. And that Tz of k is, in this case, when cos kx equals cos ky. These are the zeros of the spins that we see in this altermagnetic splitting. And so that tells us that in this theory, the altermagnetic splitting comes from this tzk, and if you estimate the magnitude, it's approximately the square root of tz times j. Okay? And so if we turn off tz, there will be no splitting. If we turn it on, there will be a splitting. But then you can see that in this context, our spin splitting is a secondary order parameter, and it's the asymmetric crystal hopping that determines it in these theories. Okay. And so in a slightly even different language, introduced by McClarty and coworkers, we can call this a Farroic magnetic octopolar order, which is being generated by this, and then the primary order is the nail. So what I'm going to look at in the case of odd parity magnetism is, again, some primary order parameter, but we're going to be interested in these kind of Farroic orders that it introduces. Okay? Yeah, go ahead. Sorry.
So I don't know. I have a small objection to this separation because in the end, if I look at the spin density and Libor, we work this out, right? You expand in spherical harmonics, so you get the dipole term, the quadrupole term, the octopole. So isn't the separation a little bit arbitrary to some extent, calling one primary and the other secondary? Aren't they just coefficients of the same?
They are, but I do want to say that we have a definite idea of what the spin splitting is, right?
I agree with that.
And so we can say that that is this order parameter. And I just want to say that this is different than Pomeranchuk instabilities where that is the driving force. Here the driving force is nil. But you're right. Morally, as you were saying before, these are the same states.
Okay.
Okay, so now let me first tell you about the minimal models that we have, and then Brian will tell you more. But you can see the approach we take. We find all space groups with Wyckoff positions of multiplicity 2, so 2 atoms per unit cell. We require that the Wyckoff site symmetry contains inversion. That'll give us the altermagnetic states. And then we include on-site Hubbard terms and then all tight binding terms allowed by symmetry by putting the electrons in s orbitals on these sites. And then you can study this within RPA, and we can do model studies of this, and we get a whole series of results. The one thing I'll point out is that we have 40 such theories, so we have 40 space groups in Wyckoff symmetry pairs, and we can get D-wave, G-wave, and I-wave altermagnets. So we have theories for all of those, and they're listed in this paper here. All right. So I'm not going to go over all the results we have there, but now I'm going to jump to the odd-parity magnetism and say that we can generalize these theories to non-relativistic odd-parity splittings. But now we have to do one small change. We get still pairs of Wyckoff positions, but now typically what is interesting are pairs related by inversion symmetry. So inversion symmetry doesn't sit at the site. It relates to 2 Wyckoff positions. Okay, but the minimal models look very similar. Okay. And then in addition, we've seen there are other minimal models which are very formally the same, and Jorn even showed more minimal models that look very similar. Okay, so now let me switch to odd parity spin splitting. And the motivation for us is when we looked at our sublattice Hubbard models, we didn't only find instabilities in RPA Q equals 0, but you can find instabilities at Q equals pi pi or Q at pi 0. And so we have these antiferromagnetic states sitting in there. And since we have these microscopic theories, we could answer kind of what I thought was an interesting question. And that is why, let's choose as an example, the cerium, nickel, arsenic, oxygen, which is an antiferromagnet with this Q vector, pi 0, why does it have p-wave magnetism? And why is that an interesting question? Well, the first point is that this Q vector is an inversion invariant point. And that means if we have an order parameter, we can characterize that typically by even and odd parity states. But now I want to make a spin texture from this that is spatially uniform, so I want to look at products of that order parameter with itself, okay? Loosely speaking. If I now look at an even parity state and a product of that with itself, that's even parity. If I look at an odd parity state, the product of that with itself is also even parity. How on earth do we get an odd parity uniform order from that? So to me, that seemed like an interesting question. And I think the answer to that question lets us classify all the cases where we can get this kind of odd parity magnetism from particular crystal structures. All right, so just to show you how we start to address this, we're going to begin with Ginzburg-Landau theory. And so here I'm going to consider a simple plus minus ordering along the x-axis. And we're going to have 2 degrees of freedom in the unit cell, site 1 and site 2. And we're going to have spins on those. That'll be our order parameter, S1 and S2. And they're going to be related by inversion symmetry. Okay? All right, and so the first thing we can do for that is we have an order parameter. We have some symmetry, spin rotational variance, and inversion. We can write down a Ginzburg-Landau free energy for this and study what kind of states are stable. All right, and so we did that. We have a quadratic terms and then 3 quartic terms. And the phases that appear depend on these quartic terms determined by beta 2 and beta 3. And this is a free energy that's actually known from iron-based materials. So Raphael has looked at it. But here are the 3 phases you get. So you get one phase where you get a spin on one site and not on another. Another one where you get the spins coplanar or parallel on the 2 sites. And then one where the 2 are orthogonal to each other. course, it's this state I'm going to be interested in, but it turns out these two states are also interesting for their own reasons. Now, I tell you that I've written down a Ginzburg-Landau theory with two symmetries, but I have lied. I am missing a term here, and I'll come back to that term in a bit, but I'll let you think about what that missing term is with the conditions I've told you, and then I'll tell you why it disappears. All right. Okay, so we have three phases. And so now we're going to be interested in what kind of Farrowick orders these three phases have. And so we can look at each of them, and these Farrowick orders are going to depend on S squared, not on S itself, because S squared is a uniform order parameter. Right, so if we look at this phase, well, we have an inversion symmetry between the two sites. And you can see clearly this breaks inversion symmetry. And so we actually have a spin scalar odd parity order, S1 squared minus S2 squared. And it turns out, just as we had submitted our paper, the Tokyo group also submitted a paper where they focused entirely on this state in itself. So this state has some interesting properties that I'll briefly touch upon later. We have this state, and this state is very familiar to many of you in the audience. So here our order parameter is S1.S2. This is even parity, S1 and S2 switch, but it turns out to carry nematic order. And so this has been well studied in the iron-based materials, and there's a nice article with two of our distinguished guests here who can tell you a lot of details about this. And then finally the phase we're interested in, we get this S1 cross S2 phase. This has a spin vector order, and again, this is odd parity. Parity switches S1 and S2, and so this becomes S2 cross S1. And this, of course, is also spatially uniform. And that's exactly what this argument here is saying, so I'm going to skip over it relatively quickly. But the point is, you get a spin vector that's odd parity, and that means that in principle from this, you can generate a fermionic spin splitting sigma z multiplied by a form factor f of k, and that in momentum space, and that f of k must be odd under k goes to minus k. So that is our odd parity spin splitting emerging from this coplanar state. And of course, the cerium, nickel, arsenic, oxygen falls into this. All right, so back to this original question, how is it that it was possible for me to generate this odd parity state when our usual intuition would say we wouldn't have such a state? Well, that's akin to asking, when is this Ginzburg-Landau energy valid? And I told you I skipped a term that's consistent with all the symmetries I mentioned before, and that's this quadratic term S1.S2. So this term is rotationally invariant under spin space, and since parity switches 1 and 2, it's an allowed term in free energy. If I include this term in the theory, then you find that this forbids both the odd parity states, this S1 cross S2 term. That state is not allowed, and this state is not allowed. Okay. And so what we need is some additional symmetry property that guarantees this term doesn't appear in the Ginzburg-Landau free energy for these odd parity states to be stable. Okay. All right, and it turns out you can show that the only place where this really happens is in non-symmorphic space groups with Q at the Brunswick boundary, and this often allows mixed parity representations. So this is subtle, but it has to do with the fact that when we classify irreducible representations of non-symmorphic groups, we're not looking at actually representations of point groups, but we're looking at projective representations of point groups, and that's where this comes from.
What is Q?
Q here, Q is as a momentum at the Brunswick boundary. It's half a reciprocal. Yeah, this is alternating. Yeah, so this is a Q that doubles the periodicity in real space. Yeah. Okay, so, and I was going to give some more explanation of this, but if you're really interested, I can show some pictures where you can see that you have two degenerate states that are different parity. And it doesn't take long to draw pictures that demonstrate that, so you get some intuitive feel for that.
So you couldn't get this at Q equals 0?
No, you can't get this at Q equals 0.
So is this the same statement as in the case of the Nick ties, that you have the Q there, and when you do the product of two reps, like at the endpoint, you end up getting some of the U's and some of the G's in the, is it the same?
In the direct product at the endpoint, you get both even and odd parity representation.
So and this is saying is just generic for any non-symmorphic with the Q.
Yeah, I'm a little bit cavalier here, and the next step corrects that. We can then go through all space groups subject to the constraint that we have inversion time reversal, identify all the wave vectors, and also identify the symmetries for which the Ginzburg-Landau theory is correct that I mentioned. So which this term is eliminated, and there's 421 of these theories. Yeah. But this gives us a systematic way of doing this. And then from that, because we've done this group theory analysis, we can figure out the form of f of k in all these particular cases. And so when we do that, we find p, f, and h wave spin splittings. And then here's a sample of what some of the tables we have. They're incredibly long. Here's some p wave examples. And then here we list the space group, the momentum point, and then which particular representation at the momentum point is relevant. So this tells you all the theories for which you have this particular type of spin splitting, kz or kx, ky, kz. This depends on permutations of which D2H you choose from a larger group often. But this list goes on and on. Okay, so this is all Ginzburg-Landau. We have a way of addressing this, but our original motivation was to come up with microscopic theories that do this. And so let's turn to that and try to understand how these microscopic theories are different than what we're used to. So first, let's look at what we're used to. So here's a usual mean field theory for a spin density wave for a single band. All right, so we have a state at momentum k. It's coupled to a state at momentum k plus q. And then we have some magnetic order that couples those two states. And we know from many studies of this that if we satisfy the nesting property epsilon k equals minus epsilon k plus q, then we get a situation that is good for supporting a spin density wave. And this has been talked about in some contexts in the cuprates. Of course, it may not be the perfect theory for the cuprates, but it's where you can see this in operation. For example, with a perfectly square Fermi surface at half filling, you'll get this nesting. All right. So
Daniel, but the nesting is a little bit off, isn't it, in cuprates?
it is a little bit off, but yeah, it is. So again, cuprates end up being a strong coupling theory, but this is just to put your mind in a certain framework so you remember how things look like in the usual case. All right, so how does this change when you add a sublattice? Okay, well, here I'm going to consider a simple one-dimensional problem where again I have a q vector that goes in this direction. I have spin 1s and spin 2s. And so here I'm going to write down the Hamiltonian that we get. And this feature I mentioned earlier is going to turn out to be important. So here is so again, the form is simple. We have an h of k. We have some other h of k plus q. And then we have some coupling between them. And here, the new feature is we have these sublattice operators, tau sub x, and this is multiplied by cos kx over 2. So now if I add q of pi to this, I turn this cosine into a sine. Right? But this is not by itself something that is, strictly speaking, legitimate. So loosely speaking, this term is time reversal invariant, but the sine term is not time reversal invariant. It picks up a minus sign. And that means that we have to simultaneously change this tau x operator, which is a real operator, to this tau y operator, which is imaginary and also odd under time reversal. And so in the sublattice theory, this term becomes a tau y term. And it turns out keeping track of this is very important for when we're trying to figure out the odd parity spin splittings. All right. We can also write down the form of m of q. And here I've written down a simple form, well, a form for the coplanar state where the two spins are perpendicular. One points along x and one points along y. So tau 0 plus tau z gives one pointing along x, and tau 0 minus tau z gives one pointing along y. But we can do this more generally. We can keep these two spins arbitrary, and then we can look at what happens to the dispersion of this Hamiltonian when we do that. Okay? And it turns out, even though this is an 8x8 problem, it actually breaks up nicely into two 4x4 blocks, which means we can do lots of analytics. We can calculate things like Berry curvatures exactly from this. And so it's a useful Hamiltonian to study these kinds of problems. And so we can then look at the three phases we found stabilized within Ginzburg-Landau theory, and we can see what does the microscopic theory say about those. All right, so first, the phase we're interested in. We get this S1 cross S2 order, which is non-zero. We find a relatively large spin splitting, which is on the square root of j times t. And so that tells us that the spin splittings will be large and that it has this nice P waveform. This Hamiltonian doesn't directly apply to that. We're taking more general Hamiltonians in this family, but this is just for illustration purposes. We can then look at the other states. This state, this is this odd parity state where we get this S1 squared minus S2 squared. We can calculate the Berry curvatures and we find that this has a spin orbit coupling free Berry curvature dipole generically in this state. So that in itself is interesting for things like nonlinear response. We can also work out what is the, what can we say about the order appearing here for this S1.S2 order. And we get this generalized electronic nematic order that shows a difference, say, between the x and y directions. And again, the magnitude of that is on the square root of j times d. So again, a large effect, consistent with what you see in the iron-based materials. How am I doing for time?
You have plenty of time.
Plenty of time. I only have a couple slides left. So, okay. So I only have a couple slides left. So I want to see. All right. Okay. So let me go over what we do next. We can go to the MagN database and we can classify which magnetic structures belong to which particular type of order. And now we have a list of materials. We can focus on some materials and see if we can say something about those materials. And not surprisingly, we followed the first paper we found and we said, let's look at the cerium, nickel, arsenic, oxygen. And then we can fit the DFT bands. This is formally, strictly speaking, 2 copies of our minimal model, but we can do a good job. We can get the Fermi surface, and then we can calculate things for that. And so here's the Edelstein effect. I'm not going to talk about that because we will hear about that in 2 talks. But we find good agreement, and we get a spin orbit free coupling Edelstein effect. All right. And then also, thanks to Raphael, actually, we found there's another material that's not in MagN data, but there's neutron scattering data that says that we have this state. And this is this lanthanum, iron, arsenic material. You replace the arsenic with phosphorus, and remarkably, you get all 3 of the states discussed here. So here is the famous nematic state that you get in these materials. Here in this region, that is the odd parity magnet, and then here is the spin scalar odd parity state. In this case, the odd parity magnet has this H wave form, and Morten Christensen and coworkers have looked at this in detail. This is what it looks like in momentum space. So this is KZ varying around, but this is the spin splitting. The spin splittings can be relatively large here, but if you're really interested in details, Andreas has a poster about this, and he's also added spin orbit coupling to tell us what happens when that is added, and there's some interesting consequences of that. All right, so I think I am pretty much out of time, so that brings me to my conclusions. We've developed a series of sublattice-based type binding Hubbard models for magnetic states that give us spin splittings. They apply to a wide range of altermagnets and now to odd parity magnets. We find that antiferromagnetic, period doubling antiferromagnetic non-symmorphic lattices allow these odd parity spin splittings. And there's many material examples. This odd parity magnetism competes with nematic, and okay, I should have changed it. It's not really multiferroic, but I should call these odd parity spin scalar states. In principle, the odd parity spin splittings can be large, and we predict an H-wave spin splitting here. And then we have actually some interesting generalizations to other states that we're currently studying in collaboration with some other groups. And I'll stop there. Thanks.
Thank you very much, Daniel, for this very nice talk. What is known about this lanthanum iron arsenic doped with phosphorus experimentally?
Okay, well, Raphael knows, but
this phase diagram is experimental.
That's experimental.
Oh, that's
from neutron scattering.
Okay,
So neutron.
So it's really good.
Yeah. Yeah. So it's a good candidate.
Okay, that's what I missed. Thank you.
And I didn't point out it's also superconducting right down here. So and on the other side too. So it may be an interesting material to look.
Yeah, just to point out that some of the referees didn't quite agree, but it is experimental about the conclusions. But anyway, can you tell me a little more about this? The third state, the one that has the non-uniform state where you have only spin on one side. You call this spin scalar odd parity. Yeah. Can you explain a little more, like what kind of So if I think of the other two, right, nematic is like B1G, the other one is going to be some, I don't know, A2U. Here it's fine because they are related by inversion, but that one is odd parity, but it has the same representation as a P wave, I thought.
Yes, A2U is right. That's the. So this will have nonlinear transport associated with this Berry curvature dipole. That's non-zero. So that's, I guess, the typical response you'd expect.
Because the other one has a Berry curvature octopole, then.
Something like
or
that.
even
Yeah.
higher.
Yeah. So you can get these states in different symmetries, and then what you're saying is true for those.
I see. Okay.
Yeah.
More questions? This is your chance. All right. If there are no more questions, let's thank Daniel again.